All right, so it's 5:31. Okay, so it's 5:31. I'm gonna get started here. I don't know how many of you can actually hear me, especially back there, but I'm gonna get started. Are there any questions about the previous lab, the lab that we did on Tuesday? Yep. Say that one more time. Can we what? Can we go over the splitter? Okay, the splitter. Okay. Yes, so we can go over the splitter. In fact, I'm going to do this homework, at this point because it's already past due, so I can do it. But you will need it for part 2, so you might want to kind of pay attention and see if you did it correctly the first time, because if you did not, then you will probably have to do it again, but this time you'll do it in the way that I want it. All right. So we'll go ahead and get started with LogicSim, and if you have any other questions about LogicSim, now would be a good time to bring up those questions, because I'm going to run LogicSim at this point. Okay, the jar, there we go. All right, so we got LogicSim. So the first thing we need to do is to create in the main circuit. We need to have the input pins, the tunnels, the gates and stuff like that. So that's what I'll do first, is to replicate the design that you see in the questions. All right, so for input pins and output pins, I always take it from the toolbar, because these have a 3-state automatically turned off, which is kind of handy, because we don't want 3-state to be used in our design. So there are 3 input pins. 2 of those are 3-bit wide, and 1 of those is only 1-bit wide. And there's only 1 output. Well, the output pins we can deal with it later. So I'm just going to stash it here. The first one is labeled X, and it has 3-bit wide, like so. The second one, I'm going to label it Y, and also make it 3-bit wide. So you need to make sure that the ordering or the relative positioning of your input pins is the same as what I want you, okay? So in the part 2 of the lab, I have some specific requirement of the positioning of the pins in the main design. And you have to make sure that your design is, it doesn't have to be exact, but in terms of which pin is on top of which one is on the left-hand side, which one is on the right-hand side, you have to make sure that yours is the same as mine, because I'll show you how I'm going to grade this one. Yes, go ahead.
Can we use extra tunnels to keep our surface?
Yep, you can use tunnels as much as you want, because the purpose of the tunnels is to clean up the design, so you don't have wires flying in every direction. Okay, so that's a good idea. So what I'll do now is I'm going to start to use some tunnels, and tunnels are under wiring. And right here. So when you look at a tunnel, it looks kind of like a pin, but it is entirely different from a pin in terms of the purpose. A pin is kind of like a parameter. If you look at a circuit as a subroutine, then a pin is like a parameter. It allows an outside circuit to interface with whatever you're designing here. A label, on the other hand, is no more than, I would say, a local variable within a subroutine. It can only be used and visible within the same circuit. It cannot be seen from outside of this circuit or from circuits that are embedded into this particular circuit. So are we okay so far with those concepts? Because I'm trying to draw a parallel between the concepts in LogicSim and concepts that you already understand in C and C++. Are we good so far? Okay. So I'm going to label this one, the same thing as X, but that has nothing to do with the input pin X, okay? Just because a label and a tunnel have exactly the same name does not mean they're logically connected. I actually have to draw a wire to connect them. And you can see that the default width of a tunnel is just like the default width of a pin, which is 1. okay, 1 bit wide, and I have to change that to 3 bit wide so that it does not complain. There we go. So now we can do a Control C here. And if I just draw this connection, it's gonna, well, it won't have a problem right now, but as soon as I change 1 bit of X, it's gonna have a problem, like so. Why? Because the two tunnels, X and X, are logically the same. They're logically connected to exactly the same bits in the entire design. So now we have a problem because bit 2 of the input pin X is a 1, which means bit 2 of the tunnel X is now also a 1, which is here, and it goes here. But now we have a disagreement because bit 2 of the input pin Y wants it to be a 0, but at the same time, bit 2 of the tunnel X wants it to be a 1. So now we have a conflict. We have what we call a bus fight. So that is why we have a problem. But this problem is only here because I have not changed the label or of the name of the tunnel to Y. As soon as I change it to Y, it is now resolved. So is that okay so far? Because I just want to show you, what a tunnel really is. It's a logical connection, so every single tunnel of exactly the same label are basically connected to the same what we call a net in the design. Is that okay?
Question.
Yes.
Why? So you're using Y twice, so the label doesn't mean anything, right?
Yes, because if I don't make a tunnel like this, I cannot use a tunnel Y elsewhere in the design if I want to. So K0 is the same way. If I want to use K0 as a tunnel somewhere else, because there may be a lot of places where I need K0, so I want to create a tunnel called K0, so it is connected to the input pin. So at this point, all this stuff here, I'm just moving it up a little bit. I don't need to refer to the pins anymore because I got tunnels of exactly the same name that I can use throughout the design. So strictly speaking, you don't really need to use tunnels in any logic design. It's just that your design can be very, very messy because you have wires flying all over the place. And tunnels is here to help you clean up all that stuff. Okay? So do we have any questions about, yes, go ahead.
What does this look like in kind of like real life circuits, like the tunnels?
The tunnels do not have equivalence in a real life circuit because in a real life circuit you cannot have you don't have wormholes in a real life circuit. So that's why you don't have that. But in terms of logic design, just from the logical perspective, they can really help make the design look cleaner. Now then you might say, well, but that's not going to be helpful because somebody's going to have to turn this logical design into an actual circuit on the circuit board, right? But we got auto routers, we got tools on an actual circuit to kind of deal with the messy part.
Okay.
So that's why it's okay,
It's the human part.
It's the human part that needs to be clean because we cannot track down complex wiring all over the place. You're welcome. All right, so now we got X and Y and K0. We have then the other tunnels. So I'm going to do the lazy thing. I'm duplicating all 3 of these. Drag it here. Change the facing to the other side, which is east. Then we can have our P, G, and Q, okay? Because in your design, you got P, G, and Q. And I'm going to do another lazy thing here. And just change the names of the tunnels, okay? So we'll change this one, the top one, we'll change it to P, which is also 3-bit wide. This one is G, which is also 3-bit wide. I'm changing the case, but I don't think that's going to present too much of a problem. And we got Q. So these terms are defined in my notes, okay? So if people are looking at these 3 and go like, I have no idea what is P, G, or Q, well, that's an indicator that you need to read the notes or read the modules again, okay? In other words, in that case, the homework has done what it is supposed to. It's a little reminder and go like, oh, you might want to read it and double check that you understand what is, what is the letter P, G, and Q representing. All right. So we got some gates here. We need a few gates. We need one AND gate. And of course, this is gigantic, and I'm going to make it smaller. And we only need 2 input pins. So I'm going to make it a requirement after this assignment that you cannot have input pins that are not connected in a gate. In other words, if you use a 5-pin gate here and only use 2 of the pins, I'm going to be okay with this homework assignment because I didn't specify that requirement. But from here on, if you only need 2 input pins, then you make the gate to only have 2 input pins and not have more input pins than you need. Why? What happens in real life when you have a logic gate that has 5 input pins, but you only connect to 2 of those input pins? What happens to the other 3? They float. Very good. Okay, so float is the correct term in electronics. But what does it really mean? It's neither specified to have a high or 1 or low, which is a 0. So it's really just kind of hanging in between. Well, but nothing is really hanging in between, okay? Because depending on the length of the wire, it is an antenna, okay? So it becomes an antenna, which now depends on, okay, did someone just turn on the microwave? Then it becomes a 1, okay? And you don't want your circuit to be susceptible to that sort of stuff, right? Somebody's phone just rang next to you and the circuit decides to do something else. That would not be good, unless it is a cell phone ringer detector. Then by design, that's what it's supposed to do. So do not leave input pins unconnected, and that's the reason why we don't want that. All right, so this is the AND gate, and we know what the AND gate is for, right? The AND gate is for G, so we'll hook up, P X to one of the input pins to this, and we'll fix the width later, and then Y to the other input pin, and then go here. All right, so it looks like we got a whole bunch of errors, but there's only one place where we have to fix it, because these are supposed to be multi-bit gates. So we are reusing the concept of a multi-bit gate from the lab that had the access code of multi, okay? And the reason why we can use a multi-bit gate is because bit 0 of G is the AND of bit 0 of X and the bit 0 of Y. Bit 1 of G is the AND of bit 1 of X and the bit Y of Y, and so on. That's why we can use a multi-bit gate to make things really simple, because otherwise you need a splitter, 3 individual AND gates, and so on and so forth. Okay, this just makes it so much nicer. P, on the other hand, is an OR gate, so we pull out an OR gate, and same thing, we have to make sure that we only have 2 input pins instead of the default of 5. And to make it not to use up as much space, I just make it a little bit smaller, and I can still make everything line up, just barely. Okay, and we'll fix the width later. It's minor issue. So as you can see, I end up with a lot of orange wires again, but everything can now be fixed with just one change. By changing the width of the OR gate, now I have all the problems resolved. So the Q is kind of the tricky one, because it looks like K0 has to hook up to Q, but not by the definition of Q. Okay, the definition of Q in class, in my notes, I use the complex equation, x not y or not xy. Okay, but that's also known as exclusive OR. And in the design, we have a third gate, right? So how do you know what kind of gate it is? It's an exclusive OR gate. But how do you know? Well, you just go to gates and you find out, oh, the shape is the exclusive OR gate. So that's how you do that. And of course, we have the same issue here. Make sure that we only have 2 input pins and make it smaller, like so. And we'll stash it here. And then we have X, once again, going to one of the input pins, and then we have Y going into the other input pin, and then the output goes to Q. So once again, we got lots of orange wires, but that's all because of the bit width of the exclusive OR gate is wrong. And we have to fix this one because it also needs to be 3-bit wide. There we go. So are we good so far with these these elements? Okay. So at this point, I'm going to take a short break from the main design, and I'll move on to K1, the sub-circuit to make K1. So in the assignment, there's instruction to say, now make a new circuit. Well, that means you have to go to Project and then click on New Circuit. Okay, so we're making a new circuit of the same design. If you make a new circuit in a different file, you can actually bring it into this file too, but that's one extra step to do it. Yes, go ahead. You can remove K0. I mean, it's here because just because PG and K0, it might be useful later. So right now it's not used for any particular purpose. All right, so we're going to make a new circuit. Okay, you go to Project, Add Circuit, and specifically I want this to be named K1. Okay, so it creates a new circuit with the name of K1, and this circuit also needs 3 input pins, P, G, and K0, and it has one single output pin, which is K1, and I mistakenly use K0 in my notes, as the name of the output pin. It's a mislabel, it doesn't do much harm, but it can cause confusion. All right, so at this point, I'm going to refer back to my assignment to make sure that I use the right ordering of the input pins. So I'm moving down, right here. So it's got P, G, and K0. So we'll switch back here and label these accordingly. P, G, and K0. And by the way, these labels are not mandatory. They're not really functional, other than it tells you what the pin is representing. So if you do not have these labels here, it's not the end of the world. But it does make the sub-circuit kind of difficult to make because you don't know which one is P and which one is G. K0 is kind of easy because that's the only one that is a single bit. Okay, but the other two are both 3-bit wires. So you have to kind of figure out which one is which one. I prefer to name every single one. And then here's the output pin. I will label this K1 just to remind myself, what is K1. Okay, so now your job is to figure out, okay, what do we do in between? Oh, wait, there's two more things to do. Because P and G's are supposed to be 3-bit input pins, so we have to adjust both of these to 3 bits. There we go. All right. So now we go back to the website, okay? Because I cannot remember, how K1 is defined. So I'm going to go to my notes, go to binary addition. Where is it? Binary addition right there. And look up, how K1 is defined. So that stuff, they're all in section 6. So you go to section 6, you scroll down a little bit, and we find how K1 is defined. So K1 is G0 OR, and then the bitwise AND between P0 and K0. Okay. So we go back to the design, go back to LogicSim, and we know what we need. Okay. We need an OR gate, and we need also an AND gate. And let me see if I can change both of these at the same time. Looks like we can. So we can change the size of both and change the number of input pins of both at the same time, which is kind of cool. Okay. Sorry? Data bits too. Yep. All the common attributes can be changed. Sorry? Yeah, you have to split. Yes. So we know the result is basically the bit OR of something, so that can go straight to here. No problem. But when you look at the equation, I don't need the entire G because I only need 1 bit out of the G because the input pin has G0, G1, and G2. I only need G0. So I need a splitter to get just G0 out. And the same thing applies to P0 because the input pin P has all 3 bits, and I just want one of them. So I need a splitter for that purpose as well. So I need to go back to the design, and this time we need to specify 2 splitters, not just 1, but 2. So we go look up get a splitter, top, yep, right there. It's not alphabetically sorted. Okay, but when you look at the splitter, the default is it has 2 bits, okay? The bit width is 2, which is not going to match our input pin. So that's the first thing we need to fix, is to make sure that it has a bit width that matches the input pins, which is 3. Now we look at this design or look at this splitter and go like, okay, how are my bits, split across the split end of the splitter, okay? So what you need to do now is to look at the individual bits and see how they are assigned to the different split ends, okay? I got 2 split ends. How do I know? Because the fan out. Fan out controls how many split ends I'm gonna have, and it can vary, okay? So all of these can change. So if you want your design to look extra clean, you can have a fan out of 1, because we really only need 1 bit out of the 3, so you don't need the other split ends. On the other hand, if you say, I don't want to mess with that, okay, I'm just going to get all 3 bits, and I'll just leave some of these split ends unconnected, that's fine too. That's your choice. Is that okay? So I'm going to use this particular approach just to emphasize which bit I'm using, okay? So move this one out of the side. I'm going to duplicate not this one. I'm going to duplicate the splitter because I need one for P and I need one for G. So I'll put one here and put one over here. Connect my input pins to both of these, okay? And of course, I have a very bad, short-term memory. I just need to read it again. So G0 is on its own going to the OR gate. So G0 just goes straight to one of the input pins of the OR gate. So that means P0 goes to one end of the AND gate, of the input of the AND gate, and then K0 goes to the other input of the AND gate. The output of the AND gate then goes to the input of the OR gate. Now we have K1 done. Do we have any questions? But we cannot really test it. Yep, go ahead.
Do we have to just disable bit 1 and bit 2 for the splitters? For this particular problem, do we have to disable bit 1 and bit 2 for the splitters?
We have no use of bit 1 and 2 from P and G.
Because when we just
You mean from the
disable it, it just creates.
what do you mean by disable? From at the
Yeah.
Bit 1 and 2.
uh-huh.
In bit 1, no, in the
Selection. The selection.
In the splitter selection?
attribute,
Yeah.
with none.
You can specify none.
Yeah, it's going to be great.
Yeah, if you specify none, you might as well change it to only have 1 split end. That makes it look nice. Let me show you what I mean by that, okay? So if you want to do it that way, I would just change the fan out to 1, and then change it so that bit 1 is not connected to the split end, and bit 2 is also not connected to the split end. So from the artistic perspective, it makes it look kind of nicer. So you can use any way, okay? So basically, do whatever you need to only extract bit 0 and bit 1. Is that okay so far? So here comes the fun part, because we need to look at the appearance of the circuit. If you look at this thing as the definition of a subroutine with parameters and the code inside the subroutine, the package or the appearance of a circuit is the prototype of a subroutine. It is just the name and the parameters and the types, okay? So that's the prototype. But you have to make sure that it does match, okay? So let me go to switch to the appearance, which is here. So this is the default, and it picks up the pin positions based on the position of the pins inside the design. But if you have moved things around after you have edited the appearance, then the appearance will stay the same while the inside of the definition has changed. So that can cause confusion. Okay? But if you're not 100% sure, one thing you can do is to click on the pin and see which one it connects to in the design. So this is a pretty handy feature, and you can double check and make sure that we have P, G, and K0 like that. And also K1 is the output. So if you click on K1, which is a little bit harder because the orientation pin is also here, but you can still click it. Does everybody see what I'm talking about? You can map the what we call the port of the appearance to the pins of the actual design. Okay? So once you have double checked everything, this step is also kind of extra, but I would do it, is to label these. There's no easy way to do the labeling, so you pretty much have to kind of do it this way. I just put things all over the place and then move them. It's easier that way than try to align everything when you type. So I'm going to move K0 here, P on the... Yeah, you can. You can change the text. You can change the font and even the color. So I'm going to put K1 over here. All right. Yep. Say that one more time. Oh, G. Yep, I got a wrong label. Let's see. Does it let me change it? Yep. There we go. Thank you. There we go. So are we good so far? So the significance of this particular step is I have turned the K1 circuit into a component. What do I mean by a component? A component like a splitter, an AND gate, an OR gate, an exclusive OR gate, just like everything else that you can pull into another circuit, K1 is just like, one of those other things. It's just like in C and C++, okay? You can write your own subroutine, right? But you can also call subroutines that are in a library, like string compare, or string AND compare, or string copy. Those are all library subroutines that you don't have to write, and they're supplied by the system. I have now written a subroutine called K1, and my main design can now make use of K1 as a component. Is that okay? Now, we did all of these in previous labs. It's just that now we have to use all of those things that we have learned in previous labs in this particular one. Yes?
If we switch the G and B port, but we still integrated it into the circuit correctly, would you dock the points?
I will not dock points, when you're making, when the interior of the design is not working, okay? It's not the way it appears to be. But when I'll show you how I grade it, so you guys can be prepared for that, okay? All right, so we got this done. We go back to main, okay? So in main, now what we need to do is to click on K1 as if it is a splitter, a pin, an AND gate, or OR gate, and then just pull it out, okay? So I'm going to pull it out here. And in order to test the circuit, you have to hook up P to this particular pin, G to this particular pin, and K0 to this particular pin. If you don't mind, being messy, you can pull these wires, okay? You can also use tunnels. So, because, we are talking about tunnels, might as well, use tunnels. So I'm going to use a bunch of tunnels here. And the other thing is you might want to get used to the concept of using tunnels because the processor design has a lot of tunnels. So, just understanding what a tunnel is going to be helpful. So we got P, G, and K0. And I just need to connect the wires like so, like that, and also like that. And then the output from K1 is now done. Now, K1 is only used internally within the main design, so it doesn't hook up to any actual output pin, but I can still test it, okay? Within the lab on Tuesday, or started on Tuesday, there was one test that says, if you make 2 out of the 3 bit zeros a 1, then, K1 should be a 1. So when I say 2 out of the 3, I'm referring to X0, Y0, and K0. Okay, if you make at least 2 out of those 3 a 1, then K1 should be turned on. Let's test it. So I'm going to zoom out a little bit just so that we can see the input pins. There we go. And I'm going to use the poke tool. So if only one is on or none is on, then K1 should not be lit. Yep. Nah, it's visible here. Yep. So if I turn on at least 2 of them, you can see how K1 is now a 1. Okay. If I have all 3 on, obviously K1 will remain to be on. If I turn off just one of them, it will remain to be on. If I turn off at least 2 of them, then it's off. So this is how you test whether your K1 sub-circuit is working or not. And the assignment also has instructions to tell you to make K2 also as a sub-circuit, K3 also as a sub-circuit, but not any further instructions of what to use those Ks for. That's for part 2 of the 3x3 homework assignment, which you'll see tonight. So are we good so far? Yeah? So what is the nice part of, since we only need 1 bit, in K1 from P and only 1 bit from G, why do I make the interface 3-bit wide across the board? Well, I'm really trying to make your job easier. Because what you can do now, okay, let me go to the select tool. If you have K2 and K3 done, and it is done according to the same standard, now we can just copy and paste it and change. Okay, let me move here like that, and get rid of K1 and then substitute with K2. So that makes it very easy to incorporate K2 and K3 into main. That's the reason why I have a uniform PG-K0 across K1, K2, and K3. So are we good so far with the first part of the 3x3 adder lab? And then there were a few questions, okay? So a few questions, one question was, can I use K1 to feed into K2? The answer is no, because that defeats the whole purpose of the carry look ahead design. The carry look ahead design is to remove the dependency of K2 on K1, K3 on K2, and so on. So we only want to feed PG K0 to all of the K circuits. Okay? So if your design has K1 feeding into K2, you need to change it. Is that okay? Yep.
What's the logic behind changing like at least one of the bit to be 0 in order to have the K1 to be 1?
Because if you look at the addition, the long addition, it is corresponding to the first column. And there are 2 additions. If at least one of the 2 additions has a carry, then you have a carry to bit 1. Okay, so let me see if I can show that using my Zerno. I got it started already, just at the wrong, not the best place, but it'll work. Okay, so we are talking about a 3-bit. Okay, this is X, this is Y. Okay, X, Y. This is Q. This is K. There's another addition here, and this is the actual result that we want, which is the sum, right? So the question now is, how do we end up with a carry over here. This is our K1. Well, you can have a carry because this one plus this one has a carry. But how do we get that? They have both to be 1s, right? Well, we can also have a carry because we are adding this one and it has a carry here, right? But how can that happen? Well, K0 has to be a 1. It's an input pin. It can be 1, right? But this one also has to be a 1. But how can you make Q a 1? The only way to make Q a 1 is X is a 1, Y is a 0, or X is a 0 and Y is a 1. So in all of those cases, you have at least 2 out of these 3 bits being a 1 in order to end up with a 1 here. So that's a good question, because it kind of maps the design back into this format of adding in binary. So yeah. Any other questions? No other questions? Yep, go ahead.
My question was more along the lines of when it comes to in the real world, when we have a 3-bit pin and a splitter, is that like 3 different wires? I guess what would that look like in a physical circuit?
Well, in a physical circuit, you cannot have a single wire that can carry multiple bits. So it's going to be 3 different traces on the circuit board anyway. So conceptually, we like to look at it as one thing because we don't have to draw a bunch of wires across everything. Yeah, but when you look at a circuit board, a single wire, a single conductor of a circuit board is a single bit. So it's just handy that we can look at a whole bunch of wires as if it is one thing because sometimes it makes sense to treat a whole bunch of wires as one thing. Yep. No, it is not always 0 because if we make K0 an input pin, that makes it possible to chain adders into a longer adder. So that's why we want to leave that flexibility and make K0 an input pin.
Is that kind of like when we were talking about earlier, if you added 2 4-bit numbers,
Uh-huh.
and they made like a 5-bit, but really it just has that carry, and if you're going to use that later, your K initial would be 1, like in that case?
So you can chain things, okay? So let me show you what I mean by that. So let's say you have a 3-bit adder here, okay? This is a 3-bit adder. And you want to add, let's say, 6 bits. But you're only limited in terms of hardware that you can only implement 3-bit adders. So what you can do now is to have another 3-bit adder. Whoops, I just scrolled. Okay, so where K3 out of this circuit goes into K0 of the next circuit. So we still have dependency now, but it's not quite as bad as the typical carry ripple method. Because what we usually do in this case is you have a 32-bit adder here and a 32-bit adder here to make a 64-bit adder. It's nice that way because if you look at the 64-bit adder, K64 is a mess compared to K32. So it's cheaper or less expensive to implement 2 32-bit adders and chain it like this. But what you lose is time. So sometimes it's a trade-off that manufacturers are willing to make. It's like, well, do I really need a single clock adder, or can I live with a 2-clock adder? And if in the application, the silicon cost is more than what it's worth, then you go like, we can just lose a little bit of time, but we reduce the complexity of silicon. So is that kind of answering the question? Okay, very good. Cool. All right. So this is what we have at this point. So the next thing I want to do is to show you how this is all going to be graded, because I want you guys to at least know the process. So this way, you know how you have to pay attention to the positioning of the pins and stuff like that. So at this point, I go to Google Drive, and you can go to the shared folder of the Google Drive for this class and get the same thing. I wouldn't do it now, okay, because you need to be kind of like focusing on what I'm doing here. And let me see if I remember where I put that. I cannot remember. Hmm? Commutator. Oh, I think I put it into this commutator thing here. Okay, there we go. Okay, so what I do is, okay, let me download the whole thing first. Okay, so I'm gonna download this entire thing. You guys know that you can download the whole folder, right? Okay, so I'm gonna right click on commutator and click download.
It's right at the bottom.
Oh, okay.
It's down there.
Yes, very good, but not all the way. Okay. Okay, there we go. And I put it into my temp folder. Open a new tab. Okay, what was the name? Commutator. There we go. Okay. All right. So the commutator example, gives you a bunch of files. Okay. There's the commutator tester, which is something that I use to grade your homework assignment. So I can show you that. Okay. Although it may not make a whole lot of sense at this point. Later in the semester, it will start to make sense. Okay. But at this point, it may not have a lot of relevance, but I will show you anyway. So commutator tester circuit looks like this, okay? And don't worry if you don't understand the entire circuit, it's just an example, okay? Down here is my, this is the way that I remind myself, how to run the code, because sometimes I cannot remember what was the option again, to test it in batch mode. Okay, so anyway, you don't have to understand the entire circuit. One part you have to understand is this is where the component being tested is. So this is the component being tested. In the original design, I have my own, correct component that I call a commutator, and it is implementing everything correctly. Okay? So the rest of the circuit, okay, not counting this thing, the rest of the circuit is nothing more than a test pattern generator. Okay, so it just generates a whole bunch of patterns to feed into the circuit being tested. Okay, all the outputs of the circuit being tested is going to one particular output pin, and the input pattern into the circuit being tested is also going to another output pin. Those two output pins can be logged when I run Logisim in batch mode. Okay, so this way, what I end up with is a file that tells me what the outputs are supposed to be like using the correct design. All right, so let me show you what it is going to give me here. So I really like this feature because now I can just copy and paste from the label itself, right? So let me select all. Control A is going to select everything. So no, that doesn't work. Okay, so it'll be nice if it does, right? Okay, but it's okay. I can. Oh, shift cursor doesn't work either. So, there's no way to do it. Say it one more time. The sidebar. Oh, okay. Okay, Control A over here. Oh, that works. Good idea. Good job. All right, so so I will get out of the GUI version. Okay, so I'm gonna save, no, discard. Okay, so this time I'm going to copy and paste that command onto the command line. So you can see it's kind of the same thing. Okay, I need to fix the path to Logisim. Okay, so give me a moment here. There we go. Okay, so the only difference between running it like this and the previous time is there's a dash TTY, which stands for tally type and table. Okay, so what it does is it doesn't bring up the GUI of Logisim at all. Okay, this is just command line, has no interaction whatsoever. But what it will do is it will run this circuit until the halt pin, okay, a pin that is labeled halt, to become 1. That's the signal for Logisim to say, we're done, okay? But it will also log the values of the output pins to a file, okay? But not to a file this time because it's going to be displayed on the screen, but I can redirect it to a file. So let me just run it and show you what it looks like, okay? Press the enter key. This is what it looks like. So the circuit being tested here is a very simple commutator, which means all it does is to say bit 1 from the input goes to bit 3 of the output. It would just kind of cross all those circuitry a little bit. Look at it as a very simple Enigma machine, a one single disk Enigma machine, okay, that only deals with 4 bits. Okay, so but it gives me a file of the correct output, right? So now what I do, so when I'm grading this, I have a program that will save this into a particular file. So I'm going to say this is the correct output, okay? So now I have a file that has the correct output. So now the next question is, so what are we going to do when we test your design, right? So when we look at the folder here, there's a shell command, which is kind of like a batch file called test, and there are 2 files called commutator. Commutator without the 1 is my design, okay? It is the correct one. Commutator 1 is a submission from one of the students. So now I have to run commutator 1 in place of commutator inside commutator tester. So it will go through the same input pattern, and it will log both the input and the output patterns. Then I have a way to compare them. Is that okay? So I need to make some changes to test because, okay, this one is actually done correctly already. Okay, so this is the command, when I say, instead of using the correct commutator subcircuit, go ahead and use the other one, use the alternative. So dash sub, basically means substitute, okay? So I'm going to run this, okay, test.shell, and this is only going to display on the screen. And of course, if I'm grading and if I need to look at the output of one file and then look at the output of another file, I'm going to miss something. So I'm not going to do that, right? So I will redirect this to being tested dot output, and then I'll do a diff. Okay, so the diff is between correct output and being tested dot output. If they're different, then it doesn't work. Is that okay? So this allows me to streamline and automate part of the grading process, okay? If it doesn't work, then I'm going to go in and visually look at something and see, is it really completely wrong, or is it just, the pins are not lined up, okay? Because if your pins do not line up, then it can cause a problem. Because if I go back to this design, not this one, one before that, this one. Okay, so if your design does not follow the same pin out as what I want it to be, then it's not going to give me the pattern. In fact, some of these connections may not even make it because your input pins is not where it is expected. So that is the reason why, in part 2 of this particular lab, you really need to make sure that the output, the pin out of your circuit meets all the requirements. So don't move those things around, just follow the recommended locations before you edit, circuit appearance. Is that okay? Does everybody understand, the importance of why I'm explaining this? Okay, all right. So now the question is, what the heck is a commutator? So you can look into a commutator. I think you can just right click and look into it. Oh, you cannot because it's a sub-circuit. You may be able to do it. Nope. Okay. So I can just show you that one too. So open temp. Yep. Where did I put in temp? Test. And within commutator, this is the correct design. This is it. As I said, it's a single disk Enigma machine with only 4 bits. Then you might ask, so what is commutator 1? Why is it incorrect? Right? So let's check out that one too. So commutator 1, which is a submission, kind of like, an example of a submission, is this. There's one wire, it's just miswired. Okay, you cannot see the entire thing. Excuse me. Okay, I'm gonna make it small. Oop. That's the agenda of my union meeting. There's no secret there, just if there were secrets, I wouldn't be falling asleep. But don't tell them. Okay, so come on, there we go. So you can see how the submission is not wired correctly. It was intentional so that the actual outputs would be different. So that's it. So are we good so far? So that brings up a good question. How are you going to test your design, and how many test cases do you think I can possibly feed to that particular design? It's a 3x3 adder with K0 as an input pin, right? So what is the total number of test cases? There are 7 bits as input, right? 3 pins, 3 bits coming from X, 3 bits coming from Y, and then there's K0. So there's a total of 7 bits. So that would bring it up to 128 possible test cases. And then the question is, Tech, are you really going to test it with all 128 test cases? And my answer is, why not? It's all done automatically. I don't have to do it. I can do it automatically. So but you can emulate my design. Okay, so for those of you who really want to get into this and go like, I'm going to spend some extra time to understand the test circuit so I can build a test circuit for my own designs. This is the bottom line, okay? So obviously, the inputs and outputs would not be the same, but what you need to do is to change the width of stuff, okay? This has a width of 4, you need to increase it to 7, okay? So when you increase everything to 7, that means the register here has to be 7-bit wide, the adder here has to be 7-bit wide, the output pin has to be 7-bit wide, and then these wires will all be different because you have to bundle 3 into X, bundle the other 3 into Y, and then the one left over is going to be K0. So all of those would be your input pins to the design that is being tested here. What about the output pins? Your output pins will consist of the sum as the output pin, which has 3 bits, and then K3 also as in one single output pin, which is 1 single bit. Okay? So you will be logging those, over here. So as far as output is concerned, you basically only have 4 bits, but you can separate it into 2 different pins if you want to. Okay? So there are ways for you to change your design so that you can actually, customize this particular test circuit to test your design with all 128 possible cases. Great. Now that you have a circuit to generate, the result of all 128 input test cases, how do you know whether they are correct or not? Just because you have 128 rows doesn't mean they're correct. So how do you know whether they are correct or not? What would be your proposal to test that? Write a C program. Okay? Write a C program to generate all 128 cases and come up with the correct result by addition in C or C++. So now you can generate, you can use a C program to generate the correct result of the log. Then you can compare the output of your C program versus the output of the logisim tester and see if they're the same. Is this a lot of logical, extra stuff that you have to do? Yeah, I would say that. So that means you don't have to do it, but if you know how I'm going to test it, and you can actually emulate the test environment yourself, the chances of you, being caught and go like, oh, I didn't know about this test case, is now 0. Yes?
If you write a program, compare the two results.
I do not have to write that program because I'm a big supporter of open source because I'm lazy. Why do the work when somebody else has already done it, right? So the tool that I use to do it, okay, let me, okay, I can stop this one here. There are several ways to do it. Vimdiff is a really, really cool program to do something like this. With Vimdiff, what you do is you give it 2 files, okay? One is the correct one, and then the other one is being tested. There we go. And it will show you the differences and highlight those. So it's kind of a cool tool. For grading purposes, it's great because it highlights, which entries are not the same, and it even highlights exactly which character is different on that row. Okay, so great tool for this purpose. But it's also a great tool if you want to if you're doing your cisp310 homework assignment, okay, and you save a version before the weekend, and now the program doesn't work anymore. This can show you all the changes that you have done over the weekend. Okay, so it's a great tool to use, if you just want to compare 2 files. It does not rely on get, does not rely on any revision control software. It is by itself, standalone, and it doesn't take up a lot of resources. I don't know whether they have a port to Windows, so if you're running Windows, you might want to look for a port of vimdiff, but there must be some other visualization tool to compare text files in Windows, so you just have to look for one. Are we good so far? So I'm giving you a glimpse of how your homework is going to be graded when you turn in the circuit, and also just a little bit of the tools involved to do this type of work. So are we good so far with the lab on Tuesday, and also what we'll be doing today? We good? All right. So we can now go back to comparison. Okay, we got about 20 minutes, which is plenty of time. So switch gear, and we want to switch to all right. So this is where we left off on Tuesday. We were talking about binary number comparison, and we were kind of hung up on how do we do comparison for signed representation. In other words, if I know ahead of time that a binary bit pattern is representing signed values, how do I compare those values? How do I know the first number, which is known as the minuend, is less than the second number, which is known as the subtrahend? Okay, so how do we determine that? And the earlier, the first attempt was only to make use of this conclusion here. If the minuend x is less than the subtrahend y, then the difference is going to be less than 0. But we also know that anything that is less than 0 has the sign bit being a 1, right? So at first we go like, ooh, that's good, because we can just look at the sign bit and know whether the minuend is less than the subtrahend, because the idea is the difference is less than 0 if and only if x is less than y. But then we ran into a problem. the problem that we ran into is, oh, but in some cases it doesn't work. It doesn't work because we ran out of representations. So let's say we're talking about the 3-bit by 3-bit subtractor, okay? And you want to subtract -3 from 2. Can 2 be represented in 3 bits? Signed. No problem, 0, 1, 0, okay? Can -3 be represented in 3 bits? If you look up the number wheel, it can be, okay? But 2 minus -3 is 5 as a positive number. Can 5 be represented as a signed number using only 3 bits? If you look up the number wheel, it cannot, okay? So that's a problem, because then the sign is actually not making any sense, because it will tell you 2 minus -3 is negative as a result, which doesn't make sense, okay? Because we have overflown the representation limits. Is that okay? So what we need to do now is to figure out a way so that we can tell whether we have ran out of representation limits. So let's see, where's my journal? I got several. Okay, there we go. This is the one that I want to use. All right, so let me just kind of go back and give you that example. This is 2, 0, 1, 0 is 2. And what is the representation of -3? One zero zero is -4, so 101 is -3. So you can just look up the number wheel. Okay, that works too. Okay, I'm gonna have to close that window. 0 minus 1 is a 1 with a borrow. 1 minus the implicit 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. So when we look at the sign bit, it is not telling me the truth, because -2 is not less than -3, and yet the sign tells me the difference is negative. So that's why we have a problem. But we can fix that problem. If I can tell when the result or the difference is overflowing, then I can combine that result with the actual sign bit and come to the conclusion correctly. Okay? And then last time in the previous lecture, I gave you something that looks like this, right? Negative minus negative can be positive or negative. Positive minus positive can be positive or negative. Minus minus positive can only be negative. And then the last one is positive minus negative can only be positive. Remember that table? So what this is telling us is I don't have a concern at all when we are subtracting a negative number from a negative number, because the sign can go in either direction. Okay, so it's not a concern. When we are subtracting a positive number from a positive number, same situation. So the real problem has to do with this and this, which means when we are subtracting a negative number from a positive number, in this case, and we end up with a negative number, we know there's an overflow. Is that okay? And when we subtract a positive number from a negative number, but we end up with a positive number, we also know that we have a overflow situation. So we have to find a way to detect that. Is that okay? Yep.
Doesn't it matter how big the numbers are? For example, you could have like -1 minus, or
The magnitude does not matter. It has to do with whether the sign of the difference makes sense or not.
okay.
Yeah, so that kind of automatically takes care of the magnitude problem. Yep. All right. So I'm going to use a different color to indicate what is erroneous, what is an indicator of overflow. So overflowing, okay, I keep touching something that, where's my journal? There we go. Okay. So the overflow situation is this, okay? This tells me we have an overflow situation. This also tells me that I have an overflow situation. Is that okay? So I subtract a positive number from a negative number, but somehow the difference looks positive or non-negative, or I subtract a negative value from a positive value, and then somehow the difference looks negative because the sign bit is a 1. So those would be problematic. Now we want to convert these into bits, okay? Because we like to look at things as zeros and ones because we can process those using logic gates. So to convert these into logic gates, I'm going to use blue here, okay? So if I use negative stuff has a sign bit of 1, positive has a sign bit of 0, positive has a sign bit of 0, and then over here, positive has a sign bit of 0, negative has a sign bit of 1, negative has a sign bit of 1. So that means every single time, if I can see the minuend has a sign bit of 1, the subtrahend has a sign bit of 0, but yet the difference has a sign bit of 0, we have a problem. It's overflowing. Or if we see that the minuend has a sign bit of 0, the subtrahend has a sign bit of 1, and yet the difference has a sign bit of 1, we also have a problem. Is that okay? So these two conditions are telling us that we have an overflow situation. Okay? So now we need to give these names, okay, so that we can refer to these, one by one. So I'm going to call the first one, x s, which stands for the sign bit of x, sign bit of y, and the last one is the sign bit of the difference, okay? I'm just giving each row a particular name so that I can use those names in a logical expression, okay? So now I want to come up with a logical expression for overflow, okay? So overflow can be defined as what? In other words, I want overflow to be a 1 in this situation. I also want overflow to be a 1 in this situation. But in all other situations, it should be a 0. Exclusive OR is not going to be helpful here because you need to make sure that the XS is a 1. When XS is 1, we want to make sure that YS and DS are both zeros. Or when XS is a 0, we want to make sure that YS is a 1 and DS is also a 1. Yes? Not XS and, okay, so we look at each one separately, okay? So let's look at, okay, I'm choosing a different color here. So let's look at this one here, okay? So this one, if I want to get a 1 when this happens, don't you think the equation is going to look something like XS? I want XS to be a 1. But I want YS to be a 0. I also want DS to be a 0. Now remember, I'm using multiplication as an implicit conjunction. So this is basically saying XS and not YS and not DS. Would that work? Would this conjunction give me a 1 if and only if this is happening? Okay. Cool. So now we need to work with the other side. I'm going to use a different color.
Well, you can just apply the not to the whole thing.
Not quite, because if you apply a not to the whole thing, and you basically have to use De Morgan's law, and then it doesn't look the same.
Okay.
So it's an entirely different conjunction. But in the separate conjunction that is that magenta? Okay. So the magenta part is going to say, I don't want XS to be a 1. I want XS to be a 0. Well, if XS is a 0, then not XS is going to be a 1. Okay? Because we want that to be in a conjunction. But at the same time, okay. We also want YS to be a 1. And we also want DS to be a 1. So are you guys convinced that the magenta part is only going to be a 1 if and only if we have this happening? Are we good so far? Okay. But the problem is, both of these can happen. Now, they cannot happen at the same time. So we just OR them. Exactly. We just say OR, then we are done. Okay, wait, let me go here, close it. Should have done that a long time ago, but I was too lazy. Okay, there we go. We put the OR, and now we are done. So are we okay with this circuit? Okay, so we got the pine needles. Okay, so the pine needles would basically be saying we got two distinct cases of the combinations between the sign bits of the minuend, subtrahend, and the difference. Okay, we got two distinct cases. The orange one is one, and then the magenta is the other one. But we need to boil these down to logic gates because we know how to do logic gates. So the orange part of the logic gate deals with the first part, where we subtract a positive amount from a negative amount, but somehow end up with a positive amount. That is telling us that we have an overflow situation. And then the magenta is the other one, where we are subtracting a negative amount from a non-negative amount, but somehow we end up with a negative amount, which is also indicative that we have an overflow situation. So now we convert everything into a logical expression. Are there any questions about this whole thing, the pine needles? No problem with the pine needles? Okay. Let's zoom out to the branch. Okay. Why are we doing this? What is this going to be useful for? The overflow flag by itself is not too useful. It has to be combined with the sign flag. One way to look at this, okay? One way to look at this is to look at the sign flag as a less than indicator, but it occasionally lies. It occasionally does not tell you the truth. Is that okay? The overflow is a lie indicator, is a lie detector. Is that okay? So now, how do we make use of, yes, go ahead.
Is this a lie detector, but confirms the negative side? Or just
It confirms the lying.
but it doesn't confirm the sign?
It is always accurate. So it doesn't give you false positive, does not give you false negative either. It is always right. So the lie detector is 100% accurate, but it's binary. So it will tell you the sign flag is lying or the sign flag is not lying. But the sign flag is also binary because the sign flag only has two answers. The minuend is less than the subtrahend. The minuend is not less than the subtrahend, right? So now how do you combine those two? So let me represent the problem, okay? We have the sign flag. The sign flag, has the ability to tell you whether the minuend is less than the subtrahend, okay? So it can give you a binary answer. It is true that the minuend is less than the subtrahend, or it is false that the minuend is less than the subtrahend, okay? But it does lie from time to time. So sometimes it doesn't tell you the truth. But then you have the lie detector. The overflow flag is a lie detector. When the overflow flag is a 1, it says, oh, the sign flag is lying. Whatever it's telling you is not true. Okay? Whatever it's telling you is the opposite of what it is supposed to be. Okay? So now how do we combine these two so that we know the truth? The truth is out there. Yep. Well, let's look at the truth table. Okay, so we'll look at the truth table first. I could have just given you the answer, and for those of you who read ahead of the class, you know the answer already. Okay, but I want to give you a truth table because I want to show you how to get to the answer. Okay, because teaching you knowledge is easy. You don't need me here to teach you knowledge. You just go to Wikipedia, right? I mean, there's plenty of knowledge out there on the internet. I'm trying to teach you how to think, how to problem solve. But I'm only teaching you how I problem solve, and that's why you need to take classes from different people to learn different techniques. Okay, so this is my technique. I look at the sign flag, I look at the overflow flag, and I say, well, is it actually less than? Okay? There are 4 possible cases. The sign flag says no, it is not lying. The sign flag says no, it is lying. The sign flag says yes, it is not lying. The sign flag says yes, it is actually lying. Is that okay? Each one is binary, can only be true or false, so we end up with 4 possible cases. So now the question is, which row is actually corresponding to the minuend less than, being less than the subtrahend? That is the question. So let's check it out. The first row is the sign flag saying not less than, and it's not lying. So the question now is x actually less than y? No, because the sign flag is telling you the truth that it's not less than. Is that okay? Let me say that one more time. When the sign flag is a 1, it's telling you, oh, guess what? The minuend is less than the subtrahend. But then you look at the sign flag with a little bit of skepticism, because sometimes it lies. So now you check with the overflow flag and say, is he lying? If the overflow flag says, no, it's good, not lying, honest, then you can say, okay, we can trust the sign flag now, right? So if you trust the sign flag and it says it's not less than, and then it's not less than. So then the L flag says, okay, it's not less than. The second row, the sign flag says, I'm telling you, the minuend is not less than the subtrahend. And then the lie detector goes like beep, 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 beep. Then what do you say? Then you say, oh, the sign flag is lying. Whatever it's saying is the opposite of the truth. Wait, the sign flag says it's not less than, so the truth is it is less than. Okay. Put a 1 here. Third row. The sign flag says the minuend is less than the subtrahend. And then the lie detector is completely quiet, meaning that the sign flag is telling the truth. So if the sign flag is telling the truth and it's saying the minuend is less than the subtrahend, is the minuend less than the subtrahend? Yes. So we put a 1 here. And then the last one is the sign flag tells you, yeah, I can tell you, the minuend is less than the subtrahend. And then the lie detector goes like beep, 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 beep. So what is the actual truth? It is not less than. Very good. Okay. So we got a truth table here. So we look at this truth table. So every time we look at the truth table, the bottom line is, can we do this using logic gates? Have we seen something like this? Many times already. What gate do we use to do this? Exclusive OR. Very good. So what this ends up telling you is the following. Oops. Okay, that works too. So what this is telling you, no, go away. There we go. So what this is telling you is, once you have the sign flag and the overflow flag, you just need an exclusive OR gate to give you the L flag. Why do we call this the L flag? L for less than, not lie, less than. L for less than. That's why. Huh? Overflow. So O is overflow, S is sign, and then L is less than. But it's only useful in the case of signed comparison. For unsigned comparison, you use the borrow flag. Unsigned uses only the borrow flag to indicate whether the minuend is less than the subtrahend. You can put this into the carry look ahead design. The concept of an adder and a subtractor, they don't really care about whether it's signed or not. They are the same for signed versus unsigned. The only time you need to know whether it's signed or not is when you need to make a decision based on, is that less than that? Then you need to use these flags.
Can I start next lecture with the complete expression
The complete expression?
of the less than?
Oh, it's really just L is, yes, that's the overflow.
Let's go. In a
No, those are just the most significant bits. The sign bit of a number is the most significant bit of that number. Yeah. Yeah. So there's no equation for the sign bit because it's just taking the significant bit out. All right. I'll see some of you shortly at the lab.
Do you remember the key for the next lab?
Okay, let me turn off the recorder
I can wait,
first.
I can walk over there with
No, it's good. Just give me a second here.
Yeah, sure.